Alright, so this is the last lecture. I'm going to do a very quick review just to remind you of what we've done in the course from beginning to end. So I'm not going to go through any of the details. I'm just going to just casually talk us through sort of what we've done. Essentially, in this course, we looked at how to solve statically determined problems for complex geometries. First off, we wanted to make sure that we have our sort of basics down in terms of what's statically determinate, what's statically indeterminate, and you'd be able to use that to help us to verify. That's important. Okay, so we have sort of this idea that the structural mechanics problem, we want to be able to handle complex geometries, so we need to really formally describe fields now. So, and a function for the displacement, a function for strain, a function for stress, and what we very quickly realize is that if you want to describe displacement in 3D, we need three functions, one for x, y, and z. For displacement x direction, y direction, z direction, and then we will describe the strain at each point. Essentially, we very quickly realize we need 6 to that and 6 for stress. That is just the nature of the symmetry of the problem that we are dealing with. Okay. If we want to try and go the approach that we've learned how to do regressing data through functions through data, we realize very quickly that in solid mechanics we have data in weird ways, and we can't just regress our displacement easily through that. So we need to fill in how does the forces relate to displacements, and that's all of that stuff that that resulted in us developing towards the strong form. Okay, so that's what we realized there. A big part of the course is to make sure that we understand what is our expectation from reality, what is our expectation from the theory that we're applying, so linealistic theory, for instance, and then we have also an expectation once we start approximating the theory, how does things look. And we need to make sure that we understand how they can differ, what kind of characteristics they can have, and make sure that we have sensible expectations of what's going on. So this is, as you've seen, plays a big role in the course. Okay. And then we started building out towards our solid mechanics kind of knowledge, having these fields, getting towards strains, making sure we're comfortable with what strains all are, that they're symmetrical by construction. Because we take the symmetric part of that displacement gradient, we essentially end up with a good understanding of stresses, how it's related to strains, 3D, plane stress, plane strain for the 2D cases. Then we want to make sure we understand how equilibrium works, how tractions are related towards the stress tensor, and then following through on this, we could relate all of this back towards our stress resultants. Okay, so to say that essentially macroscopically we might have forces, moments, and torsion, and how does that relate towards the stress components? Then that was essentially where we got to that point. Then we ended up with understanding what equilibrium was all about, getting the picture of how to put the problem together. Then we ended up with a strong form, solid mechanics boundary layer problem, 6 unknowns in terms of stresses, 6 unknowns in terms of strains, and 6 unknown functions in terms of displacement. So in total 15 unknown functions that we have to figure out, and essentially that all comes back towards having 3 equilibrium equations, 6 relationships, algebraic equations relating stress to strain, 6 partial differential equations relating strain to displacements, and this all also added up to 15. And then we have our boundary conditions. That was essentially how we got towards the strong form. Then we said, well, we need to approximate, we can't do this, solve this problem, it's way too difficult. So we did to approximate this, and we looked at essentially ways to approximate using discrete sets of points, or by essentially if we have the function but we don't have explicitly, we want to try and approximate it, we can use sort of an integral approach. And that's where we got to understanding that the integral approach, what we solve is really just the error squared. It's exactly the same as the weighted residual method, which was derived from that. Just writing the solution in a different form. This allowed us then to have the weak form. And this essentially, we know once we've solved this, we've solved the least squares problem. We've solved the integrals of the errors squared. We've minimized that error. Okay, so that's essentially what that boils down to. We could relate this in a nicer way, where initially we don't have anything but the tractions in here, and after doing some manipulation, we have now the traction as part of the expression there at the top. And this is essentially the weak form. This is what the finite element was all about, to say how do we actually solve this. And that was essentially where we ended up with this part of the course. And then we started developing the finite element method, where we brought in the idea of shape functions, n1, n2, n3. Some of them must be equal to 1 to make sure we can handle rigid body motion. There's a couple of characteristics. We constructed them in such a way that they 1 at one node and 0 at all the other nodes, so that they have very nice specific meaning. And we learned about consistent node loading. We learned about body forces, displacements, understanding the displacements are enforced exactly, the tractions are enforced approximately, equilibrium is only satisfied approximately. And as we build that up towards multiple elements, then we extended our lives from going from 1 dimensions to 2 dimensions, and essentially generalizing that a little bit further to say, this is sort of the things that we've learned in the 1D, what's mesh distortion, what's the global coordinates, what's the local coordinates, and what are their meanings in terms of two-dimensional elements, and essentially what it means to have multiple elements in terms of a global element numbering scheme, how we would assemble them, and then similarly those things can be extended in terms of the two-dimensional case. And the 2D stuff we really just focus on using code that already did all of this for us, but really trying to understand this critically, make sure we can transfer these concepts from year to year. And this is essentially what we learned in the course. Okay, so that's really a quick rundown of what we've learned, and then we started exploring largely the stiffness matrix system Ku equals to F systems that result from this. What is the meaning of the stiffness matrix? If you start decomposing it into eigenvectors and eigenvalues, what is their meaning? Understanding what are some of the flaws of some of the elements, how things can go wrong, and essentially exploring that we can symmetrize, anti-symmetry, combine with linear superposition to make up solutions and compute them in a lot more efficient manner. Okay, so that's really the rundown of that, and we ended the course there essentially with the dynamics part of understanding that there's a mass matrix that comes into play, there's a generalized eigenvalue problem, then we essentially have the vibration modes, and then we can express solutions in terms of a modal kind of fashion, where we can actually evaluate this at any time, or we end up with a situation where we have to integrate from beginning of time a differential equation, a set of differential equations up until the end. That's really what the course is all about. So I hope you have got a good overview from what I just run through here. What I want to do is quickly open up that set of notes that I posted, just to talk about a bit more detail about the where's that notes. Just quickly run you through the set of notes that I've posted, which is really just running around exploring some of the two-dimensional concepts. Okay, so let's just quickly run through this and make sure we're comfortable with more or less what's going on here. Here again, this is the kind of the weak form that we've derived now, this idea of shape functions, the idea of nodal values for the displacement, that's the unknowns that we solve. So we take this continuum problem, make it a discrete problem, that becomes a linear algebra system of equations, nice to work with. What does it mean to have strains, stresses in this environment, stiffness matrix, and then essentially loadings that you could have, body forces, attractions. And then we can explore a little bit what does four-node quadrilateral elements look like. So this is just plotting essentially a grid of a four-node quadrilateral element. This is the local coordinate system, this is the transform system, and you can see how it transforms points on this grid. That's essentially what that does for us. So we can see here that we have essentially a distorted element, because if I take steps here at different places, the rate at which it says steps, or if I let's put it like this, if I want to take a constant step here, in some places here I need to take a smaller distance, and other places at times I need to take a larger distance. That tells us already that Jacobian is not going to be a constant, and that we're going to have sort of a mesh distortion in there. Okay, and this idea of mesh distortion was that it introduced integration error, because we ended up with the stiffness matrix computations and polynomial divided by polynomial. And we could set it up into two fields, one for x and one for y displacements, so that we understand what's going on there. This is just looking at the shape functions, visualizing them for n1, n2, n3, n4 for a Q4 element. Shape functions summed together must be equal to 1 to be able to give us rigid body motions, otherwise we'll have strains invoked when we want to try and have rigid body motion modeled. This is just essentially now just extending this idea of the Jacobian a bit more formally for you, but you can see what happens in terms of if you have different geometrical element configurations, like here and here. You can ask yourself, if I take a step here anywhere in the x direction, you can see that these blocks are always going to be the same distance, and the same for the y. So this is essentially going to result in a constant Jacobian. This is also going to be a constant Jacobian. Here you can see severely non-constant Jacobians, and this non-convex element is a disaster. You can see the chaos that's ensuing there, non-uniqueness and all sorts of stuff. You can't even tell which point maps from here to here. So that breaks down the mapping completely. Okay, then let's numerical integration, looking at that in a bit more detail, how we can actually go and look at the various components that we would like to go and compute, make sure to understand what is full integration, what's reduced integration. Here just deriving some uniform tractions, varying tractions for you. So just going through the formal calculations like we've done in one of the notebooks. It's just some more examples you can work through, numerically integrating them, showing that they're the same as you can do analytically. Temperature is not important for this course, but it's nice to look at if you ever want to look at it. It's very simple to deal. It's really as simple as having been essentially a expansion that you would like to have because of temperature, and if essentially your strain is exactly the same as that expansion, the temperature wants to do, there's no constriction, then there's no stress that results. It's really the differences in that. So when you constrict stuff, stress is built up there. And then we looked at element behavior, deformation modes. Here they're just plotted now, but formally with the energies, the eigenvalues at least. Volumetric locking, we looked at that, just demonstrating to you what volumetric locking is all about. Looking at the modes, seeing for yourself that there's chaos, Poisson's ratio going up in the bending. Shear locking, also understanding that this element that's trying to represent bending, this is the way it tries to represent bending, but there's clearly a change of angle, so that 90 degree is not 90 anymore. So there's shear always that comes with when this thing tries, this type of element, this Q4 element tries to represent bending. So it's a base attempt to do bending, results in angles changing, so that results in shear, and that shear causes chaos. Reduced integration that can cause communicable modes, if you recall, essentially modes that can sort of have zero energy modes, so this thing can displace into crazy shapes without any work being done. And then we look at the dynamics. This is really just reminding you of the types of problems that you might want to work with, and understanding sort of what are the solution strategies involved. So here we're quite comfortable about the mass matrices and stuff like that. Free vibration, you can solve that kind of problem, or the modal kind of problem. You can also have forced harmonic problems there, or we can have sort of the problem where we do the direct integration, explicit or implicit. Explicit for very small time steps, explosions, impact events. Implicit allows for larger time steps, a lot more stable, and unconditionally stable algorithms as well. So it doesn't matter what time step it is, it will always solve. It might not be accurate. Okay, and then just last couple of things is about beams, not something that I worry about in this course. And then lastly, we can just quickly look at something that's called multiple constraints. And what all of this is, it allows you to have, and this is not something formally part of the course at all, but this for those of you that are interested. This is when you have sort of a roller, let's say I have a structure, a beam, but it's at 45 degrees, and I want to make sure this edge can roll up and down along that edge. NPCs is a way for you to model constraints, linear constraints, like rollers and stuff like that, that are at angles, and so they have enforce specific relationships between points. So if you imagine if you want to go down this roller, the x and y displacement that you can handle along that edge, if you want to roll along that, has a very specific relationship. NPCs is the way for you to actually model that. We'll see how it goes in the future, because I would like to make this part of the course towards the end, but I think the course is already nice and full, but let's see how things run for next year or in the future. Because this will complete sort of the content that I've envisaged for the course when I started first time teaching. Okay, that's really where this comes to an end. There's not much here that I want to highlight. Okay, that's it. Okay, all right, all the best for the exams. I hope you have fun. And yeah, we'll see that. For those of you that are gonna, obviously continue with MRN, good luck with your decisions there, and good luck with your careers as engineers. I really enjoyed teaching you, and I look forward to seeing those of you that will end up with MRN, what kind of research activities will involve next year. Okay, all the best.